Okay, so we're going to continue looking at this same system of differential equations that we introduced in the previous video. So R is denoting our rabbit population, say in hundreds, F the foxes in tens, and T is years. So this system of differential equations is modeling how the rabbit and fox populations are changing over time. And as with one differential equation, we can use the equations to make predictions about the values of our dependent, in this case, variables, both of them R and F. So we can make predictions based on these rate of change equations, even if we don't know or haven't found what the analytic solutions for this differential equation are. So even if we don't know what the solution formulas are for R and F, we can still take a numeric approach to come up with some predictions. So for example, here we're going to start with R equal to 3 and F is equal to 2. Okay, so we've got, say, 300 rabbits and 20 foxes. And we want to make a prediction for what are going to be the rabbit and fox populations 1 year from now if these are the current conditions and their populations are changing according to these two differential equations. So we're going to use two steps of Euler's method to come up with some predictions for R and F. So let's start with the differential equation for dr dt up here. And so using this differential equation, we have 3 times R, which I would plug in for 3, minus 1.4 R, which again is initially 3, times F, which is initially 2, and that gives me a rate of change of 0.6. So the RDT is 0.6. And so what the RDT is telling us is if we were to increase time by a full unit by 1 whole year, the rabbit population would increase by approximately 0.6, so by about 60 rabbits. But with one step of Euler's method, we're using delta t to be 0.5. So we're not increasing t by a whole unit, we're increasing t by half a unit. So we need to scale this rate of change, the RDT, accordingly. So we're going to multiply the RDT, which was 0.6, by delta t, which is 0.5. And you could think about when I take the RDT times delta t, the t's cancel, and what I get left is estimate for the change in R. So scaling this by half a unit, we get that delta R is therefore 0.3. So that tells me that R, which started at 3, goes up by 0.3, and now it's going to be approximately 3.3. And we do the same for the foxes. We take the differential equation, df dt, which was given by the original system, and that tells us the rate of change of the foxes is going to be minus 1 times the initial fox population plus 0.08 times the rabbit population times the fox population initially. And that gives us a rate of change for the foxes, which is 2.8. And again, since delta t is 1/2, we scale that to 1.4. And so the foxes, they started at 2, and now the foxes have gone up by 1.4, so that puts the fox population at 3.4. And that's where we are half a year later. And then we take the next step to make our prediction 1 year from now. So again, we go to dr dt, but now in place of R and F in the formula, we plug in our updated values for R and F. So I would get 3 times 3.3 minus 1.4 times R, which is 3.3, times F, which is 3.4. And that gives me a rate of change, the RDT, which is equal to minus 5.8. So we can fill that in our table. The RDT is minus 5.8, and scaling that by half a year, by half a step, that gives us a change in R of minus 2.9. So R was at 3.3, and then we drop it by 2.9. So our value for R when t is 1 is now predicted to be 0.4. And for the foxes, we have the FDT is minus f, which is at this point 3.4, plus 0.8 times the value of r at this point, which is 3.3, and the value of f at this point, which is 3.4. And doing that calculation gives us a df/dt of 5.6, which we scale by half a unit down to 2.8. So the foxes were 3.4, and now they go up by an additional 2.8, and that puts them at 6.2. So what we can see is 1 year from now, we've got R, which is 0.4. So that tells us we've got about 40 rabbits is the prediction. And for the foxes, F is estimated to be 6.2. So that means we've got about 62 foxes as the prediction. So we started with 300 rabbits and 20 foxes, and 1 year from now, this model is predicting that we would have the rabbit population would go down significantly to 40 rabbits, while the fox population goes up pretty significantly to 62 foxes.